Science Chat, the podcast where I explore the real science behind the biggest questions in the universe, as well as some of the quirkier science we encounter every day. I'm Anna, a sixth form physics student with a lot of curiosity and a passion for understanding how the world works. From the smallest particles to the largest galaxies, join me as we unlock the mysteries and wonders of the universe and explore how physics shapes the world around us. What is your favourite song, and why? It could be the lyrics, the tune, or maybe it's just the feeling it gives you. Why does this sound happy, but this sounds sad? And what do sine waves, Pythagoras and Fibonacci sequences have to do with your favourite song? Well, we'll look at all this and more in this episode all about music. Let's start with the physics of sound. What actually is sound? Well, at its core, sound is a vibration, a disturbance that travels through a medium like air. It moves as a longitudinal wave, which means the vibrations are in the same direction as the wave is travelling. If you've ever played with a slinky, you've seen this. Give one end a push and you'll see sections of it bunch up and spread out. Those are called compressions and rarefactions, and it's exactly what's happening in the air when someone claps, speaks or sings. These waves have different shapes, and those shapes determine what we hear. For example, the amplitude, or how far the particles are displaced, tells us how loud the sound is. The bigger the wave, the more energy it carries, the louder it feels. And then there's pitch, which depends on the wavelength, or the distance between two compressions. Shorter wavelengths give us higher pitched sounds, whilst longer ones give us lower notes. But here's something cool. Sometimes two sounds can have the same pitch and volume and still sound completely different. Why? Well, let me show you, or rather, let me play it for you. I'm going to play the same note, an A, on three different instruments, the violin, the piano and the guitar. Here it is on the violin, on the piano, and on the guitar. Same note, same frequency, but clearly not the same sound. That difference is called the timbre, and it's what makes each instrument's voice unique. Physically, timbre comes from extra layers in the sound wave, things like harmonics, overtones, and the way sound starts and fades. A violin, for instance, creates a smooth, continuous wave from the bow. A piano strikes a string with a hammer, and a plucked guitar string vibrates and resonates in the hollow body of the guitar. These subtle differences give each instrument its own character, even when playing the same note. Timbre is why you can instantly tell a flute from a trumpet or a human voice from a cello. It's like the musical version of a fingerprint. Now we've heard how the shape of a sound affects pitch and volume, let's go one level deeper, into the hidden structure inside every note. When you play a note on any instrument, you're not just hearing a single frequency, you're actually hearing a mix of them. There's one frequency that dominates. That's called the fundamental frequency, the note your ear picks out. But above it, there are subtle layers called harmonics or overtones. These are higher frequency vibrations that naturally occur when you pluck or bow a string, or when air vibrates in a tube for a woodwind or a brass instrument. Now, those harmonics always follow a specific pattern. They occur at whole number multiples of the fundamental. So, if your bass note vibrates at 100 Hz, you'll also hear quiet traces of 200 Hz, 300 Hz, 400 Hz, and so on, all stacked on top of each other. These overtones are a big part of what gives instruments their timbre, which we talked about earlier. A flute and a violin might play the same note, but their overtones and how strong or weak they are shape how the note feels. So, we've talked about pitch and frequency, but what happens when you put two notes together? Because the way different notes relate to each other also has a mathematical pattern, and it's what musicians call an interval, the space between two pitches. You've probably heard the word octave before. That's one of the simplest intervals. Musically, we know it as the next highest or lowest of the same note, like C4 to C5 on a piano. In physics terms, it's when the second note has double the frequency of the first. If you play an A at 220 Hz, the A an octave up is 440 Hz. It sounds similar, just higher, like they're part of the same musical family. Here's a few examples. This is C4 to C5 on a piano. Now, if you're not familiar with the term C4, C5, This is basically just because C4 is the fourth C from the left-hand side of the piano keyboard, and sometimes called middle C. So C4 to C5, i.e. middle C to the next highest C, sounds like this. And that's an octave apart. Or on a guitar, the lowest string is an E and so is the highest string, but these are actually 2 octaves apart. Now, other intervals work in a similar way. They have specific ratios between the frequencies. For example, a major third is around 5:4 ratio. That's the interval that gives chords their happy, bright feel. A perfect fifth has a ratio of 3:2. That's one of the most stable, pleasant-sounding intervals, and you'll hear it in everything from classical music to film scores. A perfect fourth has a 4:3 ratio, still stable but a little more open-sounding. And then there's the tritone, which was actually also called the devil's interval in medieval times, and it lands right in the middle of the octave and sounds super tense or eerie. That ratio doesn't come out as a neat whole number, and your brain notices. Now here's a fascinating bit. Your ears actually prefer simple ratios. That's why certain notes sound good together. Their sound waves match up at regular intervals, so your brain interprets it as pleasant. But when those waves don't align neatly, like with more complex ratios, your ear picks up on that friction and it sounds dissonant or unstable, which composers actually often use on purpose to build tension. Let me show you what I mean. This is playing the same note twice. There is no interval between them. Now an octave, as we talked about. The same note, but one frequency is double the other, and it sounds like they belong together. This is a major third. This major third gives a bright, happy quality, and it's what makes major chords feel cheerful. And there's a 5:4 ratio between the notes in this major third, which contributes to the happy feeling it gives. In contrast, here's a minor third, which has a 6:5 ratio. The minor third brings in that slightly sad feel to it. Next, we have a perfect fifth, which is a 3:2 ratio. Very stable and harmonious. And then there's a perfect fourth, which has a 4:3 ratio. This perfect fourth is a little more open, but it still feels stable and pleasant sounding. And then we have the tritone, which is a really weird ratio of 45:32. There it is, the tritone, the devil's interval, and it's tense and unsettling because the frequencies don't align neatly. So after that, you can hear how the fifth sounds smooth, the third sounds sweet, and that tritone a bit spooky. That's all coming down to maths, to how the frequencies of those notes are stacking up. Our ears naturally prefer these clean mathematical relationships. The waves line up periodically, reinforcing each other, and this is called constructive interference. But if you play 2 notes with messy ratios, their waveforms just don't align well, and this causes interference and we hear it as dissonance. That's why intervals and chords are so deeply mathematical. Music theory isn't just theory, it's a physical consequence of how waves behave and how our brains process sound. And these patterns aren't just a coincidence. Ancient mathematicians like Pythagoras were obsessed with them. Pythagoras noticed that notes with simple frequency ratios sounded pleasing. One of the coolest links is Pythagorean triplets, sets of 3 whole numbers that satisfy the equation a squared plus b squared equals c squared. You might recognise 3, 4, 5 or 5, 12, 13 from Pythagorean triangles. What's fascinating is these triples show up in music tuning and string lengths, because frequency is inversely proportional to string length. The neat geometry of these triplets can build chords that sound harmonious. For example, take the 3-4-5 triple. It corresponds to string lengths of frequencies that create a chord you can play on the violin or piano. Here's how it sounds. Notice how it sounds really pleasing to the ear and feels right. So music, in a sense, is maths you can hear. Alright, now we've heard how maths lives inside the sounds themselves, Let's zoom out a little and look how maths shapes the rhythm and structure of the music. The patterns composers use to make us tap our feet and feel emotions are all down to maths. First up, time signatures. These tell us how music is organised in time, how many beats there are in each measure, and what note value gets one beat. Most popular songs use something like 4/4 time, 4 beats per measure with a quarter note getting 1 beat. It's the heartbeat of so many hits. In fact, next time you're listening to a pop song, just try tapping along and you'll probably find it's a steady 4/4 beat. But music can play with time too. Take 3/4 time. That's 3 beats per measure, like a waltz. It gives a very different flowing feel, like this for example. And then there are more complex meters like 7/8, where the beats aren't evenly divided. It might feel a little off-kilter at first, but it creates exciting rhythms that keep you on your toes. Now you can even combine rhythms, and that's called a polyrhythm. Imagine one hand clapping in 3s and the other in 4s, which is pretty difficult to do. But this kind of rhythmic layering is common in African drumming, jazz, and progressive rock, and it's a brilliant example of mathematical complexity in music. Okay, now for something that might surprise you, maths that literally shapes the way music unfolds over time, the Fibonacci sequence and the golden ratio. The Fibonacci sequence is a famous series where each number is the sum of the two before it, so it goes 0, 1, 1, 2, 3, 5, 8, 13, 21, and so on. This sequence appears everywhere in nature, from flowers to seashells, and even the proportion of people's faces, but it also sneaks into music. For example, some composers structure their pieces so key changes, musical climaxes, or shifts happen at points related to Fibonacci numbers. The golden ratio, which is roughly 1.618, comes from the Fibonacci sequence and is often considered the most pleasing proportion to the human eye and ear. In music, this ratio can define where a crescendo peaks or where a bridge happens. It's a kind of natural sweet spot that just feels right. Some famous composers, like Bartók and Debussy, are believed to have used a golden ratio in their works, placing important moments at times that matched a special proportion. Take Debussy's Clair de Lune. While Debussy himself didn't write down, "I used the golden ratio here," musicologists have analysed the structure and found that the emotional climax of the piece occurs at about 60% of the way through, right where the golden ratio lands. The piece is around 72 bars long, depending on the edition, and the climactic moment, when the dynamics swell and the arpeggios surge upward, happens around bar 41, which is pretty much 60% of the way through the piece. That's a perfect example of the golden ratio, showing up in timing and structure, not just melody or harmony. Now let's zoom out and talk about where music happens, because space plays a huge role in how we hear sound. Acoustics is the science of how sound behaves in different environments. When a sound wave travels through air, it reflects off surfaces, walls, ceilings, floors, and these reflections interfere with the original wave. That interference can cause echo, reverberation, or even dead spots where sounds cancel out. Let me show you what I mean. I've recorded the same short scale in a few different places, and see if you can hear the difference. Here I'm in a room with a carpet and lots of soft furnishings. And now I'm as close to under a blanket as I can get while still playing the violin. And now in a room with hard floors and surfaces and no soft furnishings at all. Hear the difference? That's acoustics. In the room with hard surfaces, the sound bounces around, creating sharp echoes, whereas the blanket absorbs the sound, making it sound dull and flat. Musicians and architects work together to design concert halls where the acoustics enhance clarity and warmth. That's why a symphony sounds incredible in a place like the Royal Albert Hall. And even in recording studios, we use acoustic panels and bass traps to control reflections. Why? Because how a sound feels often has less to do with the note and more to do with the room it's in. Let's fast forward to how maths powers the music many of us make and listen to right now, through tech and even AI. When we record music digitally, we're not storing sound, we're storing numbers. A microphone converts air pressure waves into electrical signals, and then a computer samples those signals thousands of times per second. Think of sampling like taking a photo every millisecond. Each one captures the loudness of the sound at that exact moment. The sample rate tells us how often that snapshot is taken, like 44,100 samples per second in CD quality audio. Each of those samples is then stored using bits, and how precise each one is depends on the bit depth. The bit depth is sort of like how many pixels are in your photo. The higher the sample rate and bit depth, the clearer and more natural the sound. So sound becomes a sequence of numbers, literally. Now enter the Fourier transform. A bit of maths magic. In music, it's used as a method of breaking a complex sound into its pure building blocks, sine waves, their pure frequency components. So even a messy sound like a violin screech or a vocal wobble can be broken down into simple parts. This is the maths that powers everything from autotune to synthesizers. It's also how AI can listen to music and understand its structure. Once it's digital, we can shape it, again, with maths. Autotune works by measuring the pitch of a voice in real time and shifting it to the nearest desired frequency. And reverb, compression, all of those tools rely on manipulating sound wave data using algorithms based on Fourier transforms, filters, and other mathsy processes. Then there's AI in music. Machine learning models like Google's MusicLM or OpenAI's Jukebox can generate new pieces in the style of classical pop, jazz, anything. They don't compose the way humans do. They analyse thousands of musical patterns as numbers and generate statistical predictions for what comes next. So how does this contribute to the big AI music debate? Is it still art if a machine writes it? Well, the answer might be it depends on the maths behind it. A human composer uses ratio, structure and intuition even if they don't realise they're doing it. An AI uses probabilities, algorithms and training data. Both follow patterns, but one learns them instinctively and the other statistically. What do you think? Does it matter more how the music's made or who makes it? Okay, so we've looked at the physics of sound, the patterns of music, how maths plays a role in musical structures and rhythms, acoustics, and modern music tech. And through all this, it's clear to see that music is maths and maths is music. I think the connection between maths and music reminds us that beauty and logic aren't opposites, that emotion and equations can live in the same space. Music moves us, it comforts us, energizes us, inspires, and sometimes it's just more of a feeling that we can't explain. And yet beneath every melody and steady beat, there's structure, symmetry, it's maths. And I think that's kind of magical. The same principles we use to describe black holes and sound waves also explain why a chord makes us feel calm, or why a rhythm makes us want to dance. It's a reminder that science isn't cold or distant, it's part of our everyday joy, and that if you love music, you're already connected to physics and maths in ways you may not have realised, or when you play music, you are doing maths in your head subconsciously. You don't have to choose between the creative and the technical. Music is proof that you can embrace both. So, whether you're crunching numbers or strumming chords, I'm afraid you cannot escape the beauty of maths. Well, that's all for today. I really hope you've enjoyed this episode. If you have, I'd really appreciate if you could leave a rating and share with your friends. Also, go check out the Instagram page, Schrödinger's Chat Podcast on Instagram. And if you have any comments, feedback or questions, please give me an email on schrödingerschatpodcast@outlook.com. Thank you so much for listening, and I'll see you in the next episode. Bye!